we're ready now to look at concentrations. And under concentrations, we're going to talk about percent as a way of expressing concentration, molarity as a way of expressing concentrations, and then we'll do a couple of assays. There are three common types of percent solutions. There is the mass-mass solution, in which everything is done by mass. There is the volume-volume solution, in which everything is done by volume. And there is the mass-volume solution that finds particular application in medicine and biology. Now, it's important to designate what type of solution you're using. But sometimes we don't do that. And if we do not specifically designate that it's M for M or V for V or M for V, then you should assume that it is a mass-mass solution. Because quite frankly, we get kind of sloppy sometimes and don't designate that one because it's so commonly used. Let's start with the mass-mass solution. The easiest way to tell you about this is to give you an example. Suppose you have 100 grams of a 15% sugar in water solution. How much sugar do we have? Well, if it's a 15% sugar solution and the solution weighs 100 grams, then we take 15% of 100 grams and we say, okay, we've got 15 grams of sugar and we have also 85 grams of water. So we put 15 grams of sugar in 85 grams of water, stir it up. This gives us a 15% sugar solution because the whole thing weighs 100 grams. The question you might want to know is, what's the total volume? And the answer is, I don't know. I don't know because I don't know the specific gravity of that solution or the density of the solution. But I can tell you everything about mass. Now remember, in this kind of a solution, mass is used for everything. Got the idea? In a volume-volume solution, everything is done by volume. Look, consider if we have 100 milliliters of a solution that is 15% V for V alcohol and water. Well, the alcohol is 15 milliliters, so we take 15 milliliters and we add water. How much water do we add? Whatever amount is needed to bring the volume up to 100 milliliters, because it's 15 milliliters of alcohol in every 100 milliliters of solution. And quite frankly, you're going to ask the question, well, why isn't it 85 milliliters of water? And it may be, but it probably isn't. Why isn't it? When the solute and the solvent are in each other's presence, there is a relationship that is formed between them. That relationship can draw the molecules closer together, or quite frankly, it can push them apart. And which it does dictates whether the volume is going to be more than or less than the amount that we think. So what we do is we take 15 milliliters of the alcohol and we add enough water to bring the level up to 100 milliliters, so that we have 15 milliliters of alcohol in every 100 milliliters of the solution. And remember, volume is used for everything. Now let's go to mass volume. Consider if we have 100 milliliters of a 15% mass volume glucose and water solution. And I'm using glucose because this is the one that is most frequently used in medicine and biology, and glucose and water is a common one. Well, how much glucose do we have? The amount of glucose that we have is 100 milliliters of the solution times 15 grams of glucose per 100 milliliters of solution. See, it's mass per volume. That tells us then that we have 15 grams of glucose. So we put in 15 grams of glucose. How much water do we add? It's kind of reminiscent of the one we were talking about a moment ago. we add enough water to bring the volume up to 100 milliliters, so that it is in 100 milliliters of the solution, we know we have 15 grams of glucose. Medicinally, we very often talk about 5% dextrose solutions or 5% glucose solutions. That's in every certain volume, 100 milliliters of the solution or 100 cc's, we have 5 grams of the glucose or dextrose. And as I told you earlier, this designation is frequently used in biology and in medicine. Let's look at molarity, and it's probably the most important method that we use when we talk about concentrations. Molarity, by definition, is moles of solute per liter of solution. Moles of solute per liter of solution. A shorthand way of noting it is molarity is moles per liter. Yeah. Well, how do we go about making these solutions? We take a device called a volumetric flask. Now, the volumetric flask I'm showing you is one that will hold 1,000 milliliters at 20 degrees Celsius. Now, notice this line up here. That is called the fill line. And when you make a solution, you have to fill that volumetric flask so that the meniscus, the bottom of the meniscus, is exactly resting on that line. And that is the point at which you have 1,000 milliliters in this one, or 250 milliliters in a 250 ml one, and so forth. Again, that's a volumetric flask. And it will be important for you to know when you get to the lab that these flasks are calibrated to contain. I'll explain that in a minute. Calculate the molarity made of a solution made by dissolving 5.4 grams of sodium chloride in 250 milliliters of solution. We're going to use a 250 milliliter volumetric flask. Well, we first take our 5.4 grams and convert it to moles. So we take our 5.4 grams and multiply it by 1 mole over 58.5 grams per mole. That's right. That tells us how many moles we have. And remember, molarity is moles per liter. So now we're going to change to moles per liter. We've got moles. So we've got to get liters in the denominator. So it's times 1 over 0.250 liters. That's right, 1 over 250 liters. Our grams cancel, and we're left with moles per liter. And moles per liter is molarity. So the answer is 0.37 molar, or 0.37 moles per liter, or a molarity of 0.37. Got the idea? Let's calculate the molarity of a solution made by dissolving 10.3 grams sodium sulfate in 600 milliliters of solution. So we start with our 10.3 grams of sodium sulfate. And we know that 1 mole of sodium sulfate, when we add up the weights of the sodium sulfate, it's going to weigh 142 grams. Now be sure you see where that comes from. That gives us, when the grams cancel, that gives us moles of sodium sulfate times 1 over 0.6 liters. So that we're going to come out with 0.121 moles per liter, or molarity. Now, it's simple enough to do this. You take the grams, convert it to moles, and then find moles per liter, and that's your molarity. But what if we ask, what is the concentration of the sodium ion? Well, the concentration of the sodium ion is twice 0.121 molar. So the concentration of the sodium ion is 0.242 molar. Why? Well, you got to know the formula of sodium sulfate. And the formula of sodium sulfate is Na2SO4. That's also how you need to put 142 grams when you add up 2 sodiums, 1 sulfur, and 4 oxygens. Folks, questions like this are designed not only to test your knowledge of the subject at hand, such as the molarity in this particular point, but also to test your knowledge that you have to have in order to be able to do the problem, which in this case would involve being able to go from the name to the formula correctly with your knowledge of oxidation numbers. Let's go on. How many grams of sodium hydroxide are needed to make 400 milliliters of a 1.5 molar solution? Now, you want to stop, do this yourself, then come back and let me show you how to work it? Sure. Pause this, and then we'll go on when you're ready. Now remember, molarity is moles of solute per liter of solution. Therefore, when we do a little algebra, we find that moles is molarity times liters. Moles is 1.5 moles per liter times 0.400 liters. Liters are going to cancel, and that's going to leave us moles. So we have 0.6 moles then of the sodium hydroxide, but we need grams. So to find grams, we take our 0.6 moles times the molecular weight of sodium hydroxide, which is 40 grams per mole. Our moles are going to cancel, and this is going to give us 24 grams sodium hydroxide. It's really kind of straightforward, isn't it? And yes, you could have done it all in one line out there if you were comfortable doing it. There's certainly nothing wrong with doing it that way. Let's look at assays. You get in a shipment of hydrochloric acid, which indicates that it's 38% hydrochloric acid with a specific gravity of 1.19. And we want to know what is the molarity of the acid shipment. Well, this is 38% hydrochloric acid, and we did not designate if it was weight, volume, or what. If a percent solution is not designated as to the type percent it is, remember, it is percent by mass. So we start out with a volume, and I'm going to start out with 1,000 milliliters because it's 1,000 milliliters per liter, and I'd like to get liters into my equation. So I take 1,000 milliliters per liter. The specific gravity is 1.19, so I know it's 1.19 times as dense as water. So the density is 1.19 grams per milliliter. Of this, it is 38% hydrochloric acid, so I multiply it by 0.38 to find the number of grams that I have of the HCl. And then I multiply that by the number of moles over 36.5 grams, which is the molecular weight of HCl. Now let's see what cancels. Milliliters cancel, grams cancel, and I'm left with moles per liter. You see the liters over there. And it's 12.4 molar. A case of sulfuric acid has an assay of 93.4% with a specific gravity of 1.84. Now we want to know what is the molarity of this solution. It is not at all unusual for cases of things like sulfuric acid to come in with this kind of information. And it is necessary very often for us to know or to confirm the molarity of the solution. Now molarity, as you know, is moles per liter. So I'm going to use a liter of this and figure out what the molarity is. A liter is 1,000 milliliters. So I use 1,000 milliliters per liter. I'm going to find the mass of this using the specific gravity, which of course tells me that the density is 1.84 grams per milliliter. And milliliters then will cancel. Now I have the mass of this solution. I need to find the mass of sulfuric acid. And it is 93.4% sulfuric acid, so I multiply it by 0.934. This is going to give me the mass of sulfuric acid, which I can very readily convert to moles by 1 mole over 98 grams. Yes, and grams are going to cancel here and here, and it's going to leave me with an answer of 17.5 molar, or 17.5 moles per liter. There you have it. Parts per million and parts per billion. Now, we could also include parts per trillion and so forth, but it works very similarly. Let's look at a solution that is 4 parts per million sugar. What this is telling us is that in a million parts by weight, 4 parts of that weight would be sugar. Now, it's very important for you to remember that these aqueous solutions are so dilute that that tiny little bit of sugar in that million parts by weight frankly does not impact the density to any significant extent. So the key to knowing how to work these is to remember you may use the density as being the density of water. And that certainly holds true for parts per billion, in which the mass of solute is relative to a billion parts of solution, even more dilute. How many grams of lead must be dissolved, and we'd have to dissolve it in acid, but we're not going to worry about that right now, and diluted to a final volume of 100 milliliters to prepare a 10 parts per million solution? We want to make a solution that's 100 milliliters, and that solution is going to contain 10 parts per million lead. You may assume the solvent is water. We'd have to tell you otherwise. And you may assume then that the solution density is 1 because there's not enough lead in it to impact that density. So 100 milliliters times 1 gram per milliliter tells us we're working with 100 grams of solution. Now, we know that in this solution, we've got to have 10 grams of lead per million grams of solution. Where'd that come from? Yeah, that came up there in that 10 parts per million. But we don't want to deal with that much. We only want to deal with 100 grams. And when we work this out, it comes out to be 1 times 10 to the negative third grams of lead. Now, folks, you could do this by ratio and proportions. 10 grams of lead to 1,000,000 grams of solution as X is to 100 grams of solution. You get the idea? It works the same way. Assume that drinking water is allowed to have as many as 5.2 parts per billion of nitrate ion. How many milligrams of nitrate ion is allowed in 1 glass, which is 90 milliliters of this tap water? Well, we start with our 90 milliliters of tap water, and we know that since it's one of these super dilute solutions, that we can use the density of water, and this gives us 90 grams of solution. We take 5.2 grams of nitrate per 1 billion parts of water, or 1 billion parts of solution rather, times 90 grams, and that's going to give us 4.7 times 10 to the negative 7 grams of nitrate. But we were asked how many milligrams. So we take our 4.7 times 10 to the negative 7 grams, and we know there are 10 to the third milligrams per gram. So that tells us then that we have 4.7 times 10 to the negative fourth milligrams of nitrate. Now, That said, let's make it more interesting. Yeah. Same problem with a small change. Assume the drinking water standard for nitrate ion is 5.2 parts per billion. How many milligrams of sodium nitrate would be allowed in one glass, 90 milliliters of tap water? Now we go through and we do the first part just like we did before. And in so doing, we come out that we are allowed to have 4.7 times 10 to the negative fourth milligrams of nitrate ion per 90 milliliters of tap water. But let's find out how much sodium nitrate would be allowed in those circumstances. So we take our 4.7 times 10 to the negative fourth milligrams of nitrate ion and multiply that by 85 grams of sodium nitrate per 62 grams of nitrate ion. Got that by adding those atomic weights. And when we do, we come out with 6.4 times 10 to the negative fourth milligrams of sodium nitrate that's allowed. Or you can do the same thing with a ratio and proportion. 4.7 times 10 to the negative fourth milligrams of nitrate is to 62 grams of nitrate ion as X is to 85 grams of sodium nitrate. There are any number of ways this can be set up, but this is one way to do this. Dilution of solutions. Now think for a moment. When you dilute a solution, what actually changes? Well, the volume and concentration both change. Okay, but this is important. What does not change? And the thing that doesn't change is the amount of stuff you've got in there, the amount of solute you've got in there. In other words, the moles of solute. Therefore, we can say that the moles of solute before we dilute is equal to the moles of solute after we dilute, because it doesn't change. But moles is equal to molarity times liters. So molarity times liters before is going to equal to molarity times liters after dilution. Or if you will, molarity times milliliters is equal to molarity times milliliters. What volume of solution can be made by diluting 25 milliliters of 18 molar sulfuric acid to 3 molar? Well, molarity times milliliters is equal to molarity times milliliters. So filling it in and plugging it in and just going along, we have 18 molar times times 25 milliliters is equal to 3 molar times an unknown quantity of milliliters that I'm choosing to call Y. And when we work this out, Y becomes equivalent to 150 milliliters of solution. Now it's important that you remember that that is 150 milliliters of solution. All right, let's change it just a little bit. We have changed the problem to read what volume of water should be used to dilute the acid. Well, working it really looks kind of familiar. We start out and we calculate the volume of solution that we will produce. Now, knowing the volume of solution that we will produce, it seems kind of simple. Just take our 150 milliliters of solution and subtract 25 milliliters of the material we started out with, and that tells us, well, we should add 125 milliliters of water. But actually, it's not quite that simple. That 125 milliliters of water is only an approximation. Why? Well, remember an earlier discussion we had that we talked about how adding a solute and a solvent can cause different kinds of bonds to form? Molecules may move closer together. They may move further apart. It could require 125 milliliters of water, but probably not. It will probably require a little more or possibly a little less. But in any case, since we're adding sulfuric acid and water, you will remember to add the acid to the water. Well, this seems like a good place to stop for this lecture, so we will continue our study of solutions by doing a problem to kind of remind us of everything at the beginning of the next lecture. A better way to teach and learn chemistry.